Okay, so we just had a problem where we just start by going 60 centimeters from rest at a constant acceleration of 10 centimeters per second squared. And we go, well, that's it, okay? So we know the initial velocity is 0, the displacement is 60 centimeters, and the acceleration is 10 centimeters per second squared, okay? Now, most people that solved this started with the acceleration function, integrated it to get a velocity function, integrated that to get a position function, essentially, okay? It's very good, especially since we haven't yet done that in class. It shows you got your good calculus background and you're ready to do that, and that's easy enough. And of course, that applies even if you don't have a uniform acceleration, right? Now, if you do have a uniform acceleration, okay, so you could use calculus. But in this case, this is not necessary. Now, since they're assigned problems where you don't have a uniform acceleration, you got to know how to do the calculus. We haven't talked about it, but you guys are already doing it, okay? Which is very good, but I still have to talk about it, okay? So, I'll talk about that in a minute. What's this picture tell you? Acceleration is change in velocity divided by change in time, right? And your change in position is the average velocity times delta t. Of course, maybe you want to go ahead and put this in here for your midpoint velocity and even indicate how you level this thing off to a rectangle to make this rigorously valid, okay? So you have to know this because that is kind of something I think I was assigned. And then this implies two more equations that Vs squared is Vi squared plus 2a delta S, where delta S is your change in position, right? And that delta S equals Vi delta t plus 1/2 a times the square of delta t. So here are four equations, okay? And we can use those four equations to solve this problem now. Okay, so now our problem translates to V naught equals 0, A equals 10 centimeters per second squared, delta t, we don't know, delta S is 60 centimeters, right? One of these equations, at least one of these equations, contains these three quantities, right? And each of these equations contains only 4 of your variables. So any equation that contains these 3 can be solved for another one. And then any equation that has the remaining variable, you've got enough information to solve it, although you probably want to solve it using the original information, as we'll see. Okay? So, which equation are we going to use? Now I use V naught because that's what I usually use, but I'll use Vi here because V naught really usually stands for velocity at t equals 0. Okay? So, which equation are we going to use and what results are we going to get?